All right, so my research falls within asset management, but I'm going to scale out a little bit and actually bring it back into a broader construction, a broader multi-application thing. Because the reality is what we've been trying to do here in this particular research is play with symbolic regression to get around the challenge of not having enough data and trying to get a model that actually works really quickly. And that has all sorts of applications. So let me just start at the beginning. All right, so the specific work we're working on is looking at chiller plants. So we're trying to decrease energy for a series of hospitals. Started out in BC. Cooling towers are part of that system, chillers are the other part. And we were looking at trying to figure out how we could actually model and predict the behavior of the cooling towers to optimize energy. Now, a couple of different challenges we face. If you actually try and do this the old-fashioned way with white box models, you have an iterative nonlinear equation. And this guy, this KDA, is the biggest problem. This is a moisture retention coefficient. You can't measure it. You could calculate it empirically if you know every detail of how the cooling tower has been built. Just like the NTU method for a chiller, you can do it exactly if you know the whole length of coil in the chiller. Funny enough, facility managers don't let you take apart your chillers. So you can't find this out. So a lot of times you have these issues where you might have a white box model that tells you exactly how something is going to behave, but the data doesn't exist. Similarly, if you think of any of the applications that you're looking at where you can perfectly design something from the ground up, but if you come in, there's certain measurements that you can't have. How do you get around that? So we've been using a gray box model, and we actually use it with an explicit model. So we were trying to figure out what the cooling water supply or cooling tower supply temperature was going to be going to the chiller. The reason that we're doing this, I'm a mechanical engineer, so the reason that we're doing this is the colder the water you give a chiller, the more efficient it is. Right? So if you give a chiller, say, 50 or 26 degrees Celsius water, you can get a COP of about 8.5. If you give it 38 degrees Celsius water, you'll get a COP of about 4. So you get twice the energy efficiency with the colder energy, or with the colder water. Funny enough, what we usually do is we usually push our cooling towers down. They have VFDs, we run them as efficiently as possible. And then we wind up spending more on our chillers. So we're saving pennies on the cooling tower to spend dollars on our chillers, which doesn't make any sense. But we wanted to figure out actually how much energy it was going to save if we actually push the cooling towers to the maximum to be gentler to the chillers. So we created an explicit model based on these equations. So the fan speed as a function of our condenser water supply and return temperature. We had this data. Wet bulb temperature is just it's an ambient weather data. And then the mass flow rate of the condenser line, right? So this is all standard things. All we needed was the temperature sensors on the loop, which you have, and the VFD speed on a pump, right? So standard building automation system data, always limiting ourselves to data that everybody has. Now, we were trying to figure out other ways of getting around this. So like I said, you use Merkle, Pope, or NTU methods. They're iterative, they're physics-based, they require data you can't measure. So you wind up in a lot of troubles. You could also do a machine learning model. I don't know how many else has the pet peeve. It kind of drives me nuts when we have people who don't understand a domain, who throw an ANN or a CNN or an LSTM model at it, something really data hungry, and they come up with this black box model that's got no basis in physics, and they have no idea how the thing actually works. So we wanted to inscribe some of the actual physical behavior on it. So what we did is we actually went to symbolic regression. Now, symbolic regression is really cool because it actually forces you to use the data and it will actually give you the equations that best fit. You can tell it what equations or what operators it's allowed to use. So for example, you're doing something with fan speed and energy, you'll give it a cubic because you know that there should be some sort of cubic value, and maybe you'll get some sort of coefficient to see where there might be some variance from that, right? Models are compact, human readable, and they perform really well. What's wild is, and I just came from EC3 a couple of weeks ago where we presented this, you can train a symbolic regression model on 3 to 5 days of data and actually have it effective enough that you can use it. So we actually did this hospital cooling plant case. We had these two chillers. We had 15-minute interval data. This is just what we got from the building automation system. We had no supplemental measurements whatsoever. This is just for standard building automation information. Here's the cooling tower fan speed data set. And we had 72 hours worth of data that we gave to our model. Now, initially we had 6 weeks, we had 2 weeks, we played down, but we realized that 3 days was actually all we needed to get a reasonable model. And we basically said that if the speed was less than 33%, then it's not real data. It's basically the equipment turning off, because you'd never actually run a fan at less than 33% because you'd wind up with instability. It's just something that you do. So if you see like 18%, you know that you're actually running down and you're actually off, right? So we wanted to get rid of any missing data. So we had 3 days of data. We had about 288 data points. We split it out, and then we validated it with 3 one-week periods, 2 that were within season and 1 that was out of season. So we used Julia on the back end. We allowed it to actually use whatever operators it wanted out of the standard 4 and then exponents. And we used a mean, just like a loss of mean error. And this is the most efficient and the most effective surrogate modeling equation that we found. We had 2 other equations that we found with different data sets, but this is the one that performed the best. And I'll just show you really quickly. You can see the predicted is in the orange, the actual is in the blue. And it's a reasonably good fit, right? It was close enough that we were actually able to get a good sense of how fast the fans were going to have to actually be spun to achieve a particular condenser water supply to the chiller. So this is the first week. So the second week was not quite as good. But what's really interesting is the out of distribution, we were still actually quite reasonable. An RMSE of 6.2% is actually not all that bad for, like I said, 72 hours of training data, and we're now in the shoulder season instead of the peak season. So continuing to go and actually try to refine this, see how do we tune the retraining, how can we get this to do online learning. But when we're actually looking at the performance of the model across a variety of periods, we can actually realize that symbolic regression is actually really important. We're getting much more complex in terms of the types of AI that we're trying to use. And I'm basically here to be a voice kind of against the tide, suggesting that maybe we kind of go back to basics, right? A lot of us are engineers, and we've taken all of these physics-based courses. We understand a little bit of what's really going on. Why don't we bring in that knowledge and actually force the computers to actually work with us? That must be the timer, okay?
Everyone open.
All right, I've got a minute.
It's just
But future directions. So we're actually looking to apply this now to chillers, to variable speed pumps. The goal in my research group is to create a whole series of these gray box emulators that we can use to model all of the equipment in buildings and create things that we can actually quickly tune to other buildings. So we could have kind of an instance of a building digital twin or a cooling plant digital twin, put it into 100 buildings, and within 3 to 6 months, it's actually self-tuned. So this is the vision that we have. So we're really trying to figure out how we can retrain this, how we can actually bring things onto edge devices to actually start to inform kind of local control, because a lot of places don't have very sophisticated control, and actually see if we can actually make this really easy to deploy with very generic applications. Generally, we're supported by ISARC, and HVAC Angus is our industry partner for this research. And if you want to connect and hear more, that's my link, so you can get all of my contact information there.